All right, so in this tutorial, we're going to look at momentum in a slightly different way and collisions in a slightly different way to help us understand other situations where we want to look at the impact force of a collision of some sort. So I want to start us off with a little scenario. All right, so we have a dart gun, and I'll show you the dart gun tomorrow. I'm going to put a dart in it in each gun, and the only difference between my dart guns is I have a long barrel one and I have a short barrel one. And the question is, if I exert a force on them, so I'm going to draw on here, I'm going to put a force F on the exact same force on the same dart, so the masses are the same, so we'll call this mass. The question is, which dart will leave the barrel with a greater velocity? Okay, so think about that for a second. Would you choose the long barrel? Would you choose a short barrel? Would you choose it would have the same result? All right, I don't know what you chose, but here's something you might have thought about. You got a force and a mass, and you hopefully realize there's something called the second law of motion. It says A equals F over M. And since they have the same force and the same mass, they got to have the same acceleration. But does that mean they're going to be going the same speed at the end? Okay, so think about that. And if you really understand how the laws of physics play out, and it might not be obvious to you, that's okay, you'll accept that it's really the long barrel that will have the dart going faster. And you might ask why, if the accelerations are the same. Because we're looking for velocity, and velocity and acceleration are not the same thing. The velocity of the dart as it leaves depends on the acceleration, but it also depends on how much time it was feeling that acceleration, which is going to be over the length of the barrel. In other words, the air from the breath is going to push on the arrow all along here, which is a greater time than for here. Okay, so this brings up a very important point in that if we want to understand the outcome of a collision, you can think of this arrow colliding with the air coming from my breath, then we want to look at force and the amount of time. And that's really the big idea for this whole lesson, is what is the consequence of a force acting over time. Okay, but I'll get back to that in a minute. So what's the point of this? To maximize velocity due to a collision, you need to maximize two things. Most people understand you want to maximize the amount of force. So let's say we turn our attention to hitting a baseball. And I want to hit a baseball as far as possible. Well, we understand that we got to swing as hard as possible to give a maximum impact force. But what is less obvious is that we also want a lot of impact time. We want the bat in contact with the ball as much as possible, because the greater time it's in contact, the greater it feels the force, the greater over time which is going to accelerate, the greater the speed is. So we want to develop a relationship between these variables. And it all comes from the second law of motion. So let's revisit that very quickly. So we know A equals F net over M. In fact, we did this already with conservation of momentum. A is also, by definition, rate of change of velocity. So if I cross multiply these two and ignore the A, I get a very nice relationship. I'm going to take out the net part. I'm going to say F times T equals M delta V. Okay? And M delta V is nothing more than change in momentum. So what this means is for any collision, okay, so I'm sorry, mass times change in velocity is change in momentum. And so if MV has a name, change in momentum, we're going to give FT its own name. Force times time of impact is called impulse. And impulse is given the symbol letter J in our reference tables. Okay, so we have a new definition, impulse, and we're going to use it to understand outcomes of collisions. Okay, so a large change of momentum requires an equivalent large impulse. That's the idea. In other words, I could rewrite this as J equals delta P. Okay, if Ft is the same as J and M delta V is the same as delta P, this is a nice little statement. The impulse given to a object is equal to its change in momentum. What do we mean by impulse? Well, it's not just a force, it's a force multiplied by a time. Okay? And a large impulse can be applied by having a large force and or a long impact time. So that's the cause. So in the problem above, even though the force was the same, I'll take that back. Yeah. No. There's a number of things that were the same. I think what I want to say here. Even though the impulse was the same, it wasn't. Okay, let me go back. Okay, even though the force was the same, that's what I want to say, the longer barrel gave it a longer impact time. Therefore, giving the dart a greater change in momentum, because a force times time is an impulse, and an impulse is equal to a change in momentum, and therefore greater final speed. Okay, and that's something you want to understand. This is, in sports, this is given the term follow through. So when they ask you to follow through, what they're basically saying is exert a force for a greater period of time. A classic example is a baseball pitcher. Okay, let's say the pitcher wants to hurl the ball as fast as possible. Okay, what are the two things that person does? Well, A, they move their arm with as great a force as possible, as great a speed, right? That goes towards the amount of force you exert on the ball. Okay, in other words, the faster you move your arm, the greater the push. And then if you ever watch a baseball player do a wind-up, okay, they move their arm way back initially, and then they hurl it forward. In other words, they move their arm over a great distance, and that's what the wind-up is. Okay, so the wind-up pushes the ball for a greater time. So you don't just flick your arm when you want the ball to go fast. You move it over a great distance, which means you're pushing it for a large period of time. So we have a large F, we have a large T, and that goes to a large change in momentum of the ball, which translates to a large change in velocity. The mass is staying the same. Okay, another application we find in sports is maybe less obvious to you, but if you ever watch speed skating, usually in the Winter Olympics, around 20 years ago, world records started to be shattered because the Dutch introduced a new type of skate called the clap skate. And the clap skate is shown right here, where the difference between a regular skate and a clap skate is, in the clap skate, the heel, the blade of it is not attached to the heel. And there's a little hinge here to snap it back. And the reason why the skaters got better at time is with each push, right? That's how they propel themselves. That's their power, where they get their power from. So with each push, the clap skate stays in contact for a longer period of time. So in contact, that's your force, right? For more time. All right, by having the skate on the ice and not pulled up by the heel, then we have a big FT. That's an impulse. And what's the consequence? We get an equivalent change in momentum, which is equal to a delta V. So, in other words, when you're pushing, by pushing for a longer period of time, because your skate's in the ice for a longer period of time, you get a bigger change in velocity. Okay, so now we're going to look at the verse for this. So we have situation 2. I don't know if you ever watched the movie or this TV show Jackass, but it was about a bunch of guys that did some really crazy things, crashing and trying not to hurt themselves too badly. So I've just picked up from here. And this is going to a collision again. So let's say one person, Steve-O, gets hit by a bus that's going 10 miles per hour and suffers multiple fractures. Whereas his accomplice, Johnny Knoxville, gets hit by the same bus, moving the same speed, but only gets bruised. What might have been different about the collision to have the impact force on Johnny be much less? In other words, if he escapes the collision without much damage, the bus didn't hit him with as much force. Okay, so there's a lot of things that could have been different. All right, it could have been a mattress on the bus. Mattress, let's say, for a bumper. Or Johnny was cushioned. In other words, he was surrounded by a bunch of cushion so that when the bus collided with him, he didn't feel as much impact force. Maybe he rolled with the collision. Okay, and that's a very important technique. If you ever fall, let's say while skiing, you don't just stiffen up, you roll with it, and the idea is you change your momentum over a greater period of time, and that means you have less force. Okay, and this is going to be a very, very important result. So in both cases, the bus will apply the same impulse. Okay, now you should be asking, why would it apply the same impulse? This is a little bit more difficult to explain, but I'll talk about it now, but we can clarify in class. We know it has to apply the same impulse because the change in momentum of the bus is going to be the same. And if the change in momentum of the bus is going to be the same, then it has to have the same impulse. Okay, why did it have the same change in momentum? Because it was coming in with the same momentum in both cases. And if it hits the same person with the same mass, it's going to have the same change. So we have the same change in momentum. Now remember, impulse is equal to force times time. So by getting hit by, let's say, a cushioned bus, Jami experiences a collision for a longer period of time. In other words, because of the give in the cushion, it pushes on him for a longer period of time, and therefore he'll experience a smaller impact force. Okay? Or put in general, for a given change in momentum, to minimize impact force, you must maximize the time over which the momentum changes. And this time is usually called give. In other words, the greater the give something has, the more time over which it stops the object, and therefore it has less impact force. Okay, so I'll do an example of this in a second. So let me just first do a summary of the key equations, because it looks daunting, but it really gives you a huge choice of how to approach problems. So at the heart of it, we have an impulse, or a force multiplied by time, equals m delta v. And I got that right from the second law of motion. So on the cause side, Ft is called J. Okay, so I'm going to call this the cause. And then this side is called the effect. But they're all mathematically equivalent to each other. So m delta v is the same as change in momentum. And change in momentum can be thought of as final momentum minus the initial momentum. And that can be thought of as m delta v, mvf minus mvi, but I'm not going to write it here. So you have a string of equations right here that are all mathematically the same. So when you go do problems, you just have to pick what information you have, what you're looking for, and then choose the appropriate equation. It's actually very easy once you get the hang of it. So let's just finish up with an application problem. So you have car A has a certain mass, moves with a certain speed, crashes into a brick wall. Car B has the same mass, same speed, but crashes into a haystack. Okay, so if you were in those situation, which one would you rather crash into, a haystack or a wall? Well, I'm pretty sure you'd say the haystack. Now we're going to see why that is. Okay, so which car has a greater change in momentum? To help us understand which is better to hit, we're going to answer these series of questions. Well, the change in momentum, delta P, can be thought of as a lot of different ways. The easiest way to look at that is m delta V, and it's going to be the same for both, because delta V is going to be the same. Delta V is the same for both, because you're coming in with the same initial speed and they're coming to a stop, so it's going to be the same. So which car had the greater change in momentum? They had the same. So which car had the greater impulse acting on it? Impulse is right here. Well, what do I compare it to? Well, I don't know anything about F and T yet. Do I know anything about m delta V? Oh yeah, we just talked about that. So m delta V was the same for both, so it feels the same. Both cars get the same impulse because they had the same change in momentum. Which car took more time to stop upon impact? Well, that's where the difference between a brick wall and a haystack comes in, okay? It took more time with the haystack because it has more give. So which felt the greater impact force? Well, that's where we can use the idea of F times T equals an impulse. So if the impulses are the same, so let's do car A.